Alright, here we are with the week 2 homework for DC. I'll be doing this homework each week, and in some weeks I'll do a bit of a video overview of the homework in the after event. So let's have a look at this. We have a milliammeter at 58.2 milliamps. We've got 3 resistors in circuit. 68, 47 and 33 ohms. Now what I've done, I have redrawn the circuit over here on my paper, and I expect everybody to use graph paper to do their solutions and list them clearly, A, B, C, D, with full working like you can see here. Now I've labelled it, DC Week 2 Homework, page 1 of 2, February 25, 2018. Just in case this is around for a few years. Alright, so the first question said, what's the calculated? Now that word calculated, that means that we're going to have to run some maths on this. I mean, it'd be easy to look at that and say, what's the calculated? What's the value of current? Well, you could look at that and say it's 58.2 milliamps, but it says, what's the calculated value of current in this circuit? And that means we've got to run some maths. That means we had to add these values up. They came to 148 ohms. And then we had to get the 9 volt supply and divide it by 148 ohms to get 60.8 milliamps. Second part, B, is there a difference in the calculated current and the measured current? Well, the measured current is here on the meter. It's measuring 58.2. But we calculated 60.8, so what's going on? We've got a 2.6 milliamp difference due to something going on with, well, you could say, look, either the leads or the meter, but I'm thinking these leads are pretty short and there's nothing said in the question about the leads, so that voltage drop, and it must have an associated resistance, and there's a drop in current there as well because of that extra resistance in the circuit caused by the milliamp meter. What is the total resistance of all 3 resistors? Well, we had to know that to work out part A, and that's 148 ohms. Part D, what voltage would you measure across the 68 ohm resistor with the current meter in circuit? And that's repeated here for E and F, the 47 ohm and the 33 ohm. So what I've had to do, I had to get the, it did say with the current meter in circuit, we're back to our 58.2 milliamps. So multiply V equals I times R times 68, 3.95 times 47, because Kirchhoff's current law says that the same current flows through every component in a series circuit. So it's a case of just getting that one current and multiplying it by each resistance. And we get the 3 voltages. And then there's a bit of a check that I've done here. I've added them all up. And now, if we didn't have some funny things going on here with the meter, we would have added up to exactly 9 volts, but it appears that we've got the best part of 400 millivolts dropped across that meter. We've lost 400 millivolts in the circuit because instead of having 9 volts, we're down at 8.6 volts. So G, do the 3 voltages add to 9 volts? No, they certainly do not. They only add to 8.6. 400 millivolts different in H. And what's it due to? It's due to the current meter, I subscript M, R internal. Question I, if you think some voltage has dropped across the meter, explain how this can be so. Well, I've drawn a resistor symbol there and I've said R internal, it's the meter resistance. J said, if you answered yes, what voltage has dropped across? Well, we worked that out before. 8.6 is 400 millivolt difference, so there's the answer, 400 millivolt. In K, if in L you answered yes, what calculated resistance must the meter therefore have? R equals V on I, so we can apply this here. We know that we've got 400 millivolts dropped across that meter, and again I'm saying there's nothing lost in the wires, so it can only be across the meter. And I mean, all meters, we know that milliamp meters have to have a low, very low, extremely low internal resistance to work properly in the circuit, so they don't interfere with the circuit parameters. But there's always going to be some cost associated with putting a milliamp meter in circuit, and we saw that in the very first lab that we did in class. We had the same sort of mystery going on, so this builds on that, of course. 400 millivolts divided by 58.2 milliamps, 6.873 ohms across that meter. And then what have I done there in L? Removing the current meter from the circuit, redraw the circuit and show all new voltage values across those resistors. What have I got here? 4.13. So that's without the meter this time. So now we've had to do the calculations based on 60.8 milliamps. You can see I've redrawn the circuit with no meter in the circuit. So again, cross multiplying those, 60.8 milliamps times 68 ohms equals 4.13. 60.8 milliamps times 47 ohms, 2.85, and 60.8 milliamps times 33 to get 2 volts. In part M, the question was, what would be a suitable internal resistance for the new current meter? Why? And show an example with maths. Well, look, I'd like to see the resistance in the meter down in the micro ohm area, but sometimes that's going to be very impractical. In our multi-sim or Circuit Maker 2000 simulation package, of course we're down at 1 micro ohm, I think it is, for the default internal resistance in a current meter, but in practical terms that's probably rarely going to be the case. So, you know, we had 6 ohms or 6.8 ohms. I've done a calculation here, 6 divided by 148. That's like 4% error with the original meter the way it is. To get 1% error, I'd have to multiply this 148 ohms by 0.01, and that would be an internal resistance of 1.48 ohms. But, you know, if I put 1 ohm, and I'd like to think that that current meter is, I mean, it's a milliamp meter, so it's going to have a lot of very fine wire in it to measure milliamps, so you're not going to defeat all of that resistance. If we put 1 ohm into the current meter and say, you know, that's where it's at and that's what we'd like to have, that would work out to be 0.67% error, so that'd be much more ideal. So I'd have to say then less than 1 ohm of resistance in the current meter I'd be probably reasonably happy with. The sum of distributed voltage drops, what was this? State Kirchhoff's voltage law. Well, look, in a nutshell, the sum of the distributed voltage drops in a circuit adds to the sum of the total voltage sources. But of course, we'll do a PowerPoint on this, and we do that in week 3. And we examine this and we look at the potential rises and the potential falls, and then we see that the algebraic sum of the potential rises and potential falls is equal to 0. And it's just a little bit different way of putting it, but in a nutshell, when we first teach this, I've always expressed it in this way because I do think it makes a little bit more sense. Alright, that'll do for video number 1. I'll do a second small video with the homework on question 2, because question 2 of the homework is a little bit more complicated because it's done using conductances more so than resistances, and there's a couple of pitfalls that you can fall into there. So I'll wind this up now. Check your homework against the answers that I've given, and then have a look for video part 2. Thank you.